Okay, this time, what happens when you take two atoms and combine them? And then, what happens when you take billions of atoms and combine them into a crystal lattice? What happens to all of these electron orbits in that case? Well, if we take two sodium atoms, both in the ground state, and bring them together, what happens is a phenomena called band splitting. These orbits here, which are nominally at the same energy, if you combine the two sodium atoms together, the two energies split very, very slightly. And in the ground state, both of these electrons would then drop down and be the two electrons filling up the lower energy of these two orbits. It's these higher energy electrons which are furthest away from the nucleus, and therefore more likely to be affected by another sodium atom which is brought close together. And the orbits of these outermost electrons are no longer purely determined by going around its own nucleus. You can think of those orbits as kind of including both of the nuclei of the electrons. So whereas the lowest energy electrons, which are the ones closest to the nuclei, tend to be tightly bound to its own atom, the outermost electrons are much wider space. They're more able to move throughout the entire solid structure. And these orbits can encompass several nuclei. You can extend this idea to have an entire lattice of nuclei. I'm saying lattice because in a structure of most materials, the atoms are arranged in a regular pattern. And what I've tried to illustrate here is the outermost electrons, which are now in orbits which are affected by several of the neighbouring nuclei as well. And you can think of some of these orbits as being non-localized in space, or at least not localized to any one atom. I should warn you that if there are any physicists listening to this, they might be having a bit of a fit at the moment. I am making rather coarse simplifications, just trying to give you a mental model of a way in which you can think about how these orbits work in a multi-atomic block of material. The innermost orbits, very close to the nuclei, tied to the individual atoms. The outermost electrons, not so much. They are freer to move around the whole structure of the solid. Now, in the case of something like sodium, where you have some energy levels which are completely full, quite close to the nucleus, and then have these energy levels which are only half full. There's only one electron in an orbit which can contain two, some distance away from the nucleus. Then if you start putting a whole load of sodium atoms together and get a whole load of bands or possible orbits here, only half of which are full, the difference in energy between these bands is tiny. So it's quite likely in these cases that the whole crystalline structure will not be in its ground state with all of the electrons in the minimum possible energy levels. It would just take a tiny additional amount of energy to move one of these electrons up to one of the neighbouring states, and it becomes important for the properties of the material to be able to predict the probability that any particular orbit is occupied. And there's an equation that we've got which can tell us exactly that. The probability that any particular orbit with any particular energy is occupied. It's called the Fermi Dirac equation. And it looks like this. It's the probability that an electron orbit is occupied as a function of a parameter known as the Fermi level, the Boltzmann constant, K, and the absolute temperature T in degrees Kelvin. Now we can see how this works a bit. Supposing T was 0. So we're at absolute 0 in temperature here. That would mean that the probability of occupying a state is 1 over e to the power of E minus the Fermi level divided by 0 plus 1. Well, if the energy of the state of interest is greater than the Fermi level, then this would be e to the power of positive infinity, which is infinity, so the probability of occupation would be 1 over infinity or naught. This is only for absolute 0, if E is greater than the Fermi level. However, if the energy is less than the Fermi level, then this would be e to the power of minus infinity. E to the power of minus infinity is 0. So the probability of occupancy of a state would be 1 if E is less than the Fermi level and you're at absolute 0. And if you plot this on a graph, you get this black curve here. Now, as the temperature increases, what happens if you plot this distribution is that this steep cutoff begins to soften. And you have areas here below the Fermi level at which the probability of occupancy is not 1. And you have areas here above the Fermi level at which the probability of occupancy is not 0. So these are cases where you are no longer in the ground state. Some electrons have more energy than some of the gaps which they could drop down into. Most often in these talks, I won't show the distribution like this. I'll actually show it rotated 90 degrees so that we have probability along the x-axis and energy along the y-axis. And then it looks like this. But that's the only difference between this slide and the previous slide. I've just rotated the graph. Doing it like this, with energy on the y-axis, means that I can superimpose these curves on those energy band diagrams that we were seeing before. For example, here I've superimposed the probability of occupancy, that's these red dotted lines, on the possible energy states in a series of different types of solid. Remember what this red dotted line means? Out here, where it's 1, that means that these states are completely occupied 100% of the time. And when this curve gets down to 0, it would mean that these states are never occupied. They are completely empty. But a state here, an orbit, would be about 50% probability of occupancy. So half of the possible states here at the Fermi level would be occupied and half would not at any one time. You may have noticed the title of this slide, Put in Order of Increasing Conductivity, because we can use these diagrams to predict whether these materials are going to be able to conduct electricity or not. B, for example. Well, B has a lot of states down here which are completely full. And if all of the states are full, then electrons cannot move because they've got nowhere to move to. Up here, there are a lot of possible states which are empty, but there are no electrons with that amount of energy to move into them. So electrons cannot move up here in these states, and they cannot move down here in these states, so that this material is going to be an insulator. It's not going to be able to conduct electricity. C, this material, on the other hand, can conduct electricity quite easily, because all of the electrons around this energy here have got empty states that they could move into. And some of those empty states would be associated with being in different places in the lattice. So those electrons would be able to move from one state to another state and another state and move throughout the lattice fairly readily. Current can flow. That's going to be a good conductor. A. Well, A is a type of material in which the Fermi level happens in a gap between states, but not a very big gap. I'll draw this out in a bit more detail. The band up here, the band of possible states just above the Fermi level, is known as the conduction band. And the band of electron states just below the Fermi level is known as the valence band. The terms are slightly confusing because you might think that the conduction band is where all of the electrical conduction happens, where all the current flows, but actually it's not. Some current can flow due to electrons moving in the valence band as well. And if I have a Fermi distribution which is doing something like this, I've got a few electrons up there in the conduction band, and they can easily move, so you can get some current caused by these electrons moving, but not that much current because there aren't very many electrons up there. Similarly, you have a few gaps here in the valence band, and you can get some movement due to those, with electrons moving into those gaps, but not that much because there aren't very many gaps there. So this material can conduct electricity, but not very well. And this material, material A, we'd call a semiconductor. One property of semiconductors that we can predict from this theory, and which turns out to be absolutely right, is that the conductivity or the resistance of a block of semiconductor is a very strong function of temperature. Because if I increased the temperature, then the Fermi Dirac distribution would smooth out a bit and would look a bit more like that. Higher temperature, you've got more electrons up here in the conduction band, so more current flowing, and more gaps here in the valence band, so more current flowing as well. I can show you a little animation of these ideas. Here we have a conductor. Its valence band is completely full, but there are quite a lot of electrons up here in the conduction band. So if I tilt this slightly, which would be the result of putting an electric field on, and press start, we get quite a lot of current flowing, as all of these electrons quite happily move from one state to another associated with somewhere else in the lattice, and they're moving through. No problem. An insulator, on the other hand, has a large gap between the valence band and the conduction band, and the valence band is completely full. Net result, put an electric field on, press start, and nothing happens. There's no current in the conduction band because there are no electrons to carry it. There's no electrons moving in the valence band because they've got nowhere to go. Every possible state is already occupied. And then there are semiconductors, which don't have a lot of electrons in the conduction band and don't have a lot of gaps in the valence band. But they do have a few, so if you put an electric field across them, there will be some current flowing. If you look at the valence band, it's sometimes easier to think of what's happening, not in terms of the electrons moving in this direction, but in terms of these gaps, sometimes called holes, moving in the other direction. It's something that solid-state physicists often do. They talk about the movement of holes in the valence band. But what's actually happening is electrons are moving in the other direction. Before we leave this topic, just want to say something about the definition of the Fermi level. The actual definition of the Fermi level is the average amount of energy required to add an electron into the system. There doesn't have to be a particular state, a particular electron orbit with that energy. Okay, next time we'll look at conductors in a bit more detail and derive a model which predicts what the resistance of a conductor should be. Okay, next time we'll look at conductors in a bit more detail and derive a model which predicts what the resistance of a conductor should be.